Where'd you get this? The machine? You want one? No. Here. Take one. I don't want it. Good. I don't want it. Just take one. No, stop, Chris, stop it.
Open the valve and he bounced off some respirator thing into the patient.
So the motion of the junior mint, is that free fall? What do you guys think? All right, so use the chat option for this one. Okay, is this free fall? Yes or no? Most of you guys will say yes to this one, right? So you will say this is free fall. How about this one? Do you think this is free fall? Yes or no? Now, most of you guys will say, yeah, this is free fall only on the way down, right? How about this one? Do you think this is free fall? Just throwing the ball into downward traction? And most of you guys will say, no, this is not free fall. Okay, so those of you guys who say this is free fall, you're right. Give yourselves 5 points for that one. Those of you guys who said this is free fall only on the way back down, give yourselves 1 point for that one. Those of you guys who said this is not free fall, don't give yourself any points. Okay, this is free fall, so is this one, so is this one. All right, so when does this become free fall? This becomes free fall as soon as the ball leaves my hand. As soon as the ball leaves my hand, it turns into free fall. That's what it means. So what happens when the ball leaves my hand? Gravity takes over. So free fall is the motion under the influence of gravity and gravity only. So it doesn't matter that the ball is falling or being pushed on or thrown in the downward direction or sideways. As soon as gravity takes over, it becomes free fall. So the definition of free fall is the motion under the influence of gravity and gravity only. Right, so remember the guy inside the elevator? He's on the 10th floor. He gave us neck. He had a broken neck. Okay, so you'll find out, but whatever the theory that you came up with, the beginning of the semester was wrong. Or it wasn't. Some of you guys came pretty close, but it's still wrong.
LA firefighters are
so that's one of the things that we'll get to discover at the end of this.
waiting for backup. The dogs are growing impatient. Watch as they tremble in
oh my God, the building is on fire.
fear, ready
We got two boxers.
to leap 3 stories to street level. Their chance for survival is slim.
So these dogs are about 30 to 35 feet up. If they have to jump, what are the chances that they will survive? Is it good or is it bad? What do you guys think? What are the chances of survival? What are their chances of survival?
It's pretty bad.
You would think so, right? A lot of people think that 8 dogs are not going to be able to survive something like this. This is like jumping from the 3rd floor of a building. What are the chances of survival for a dog? All right, so according to Fox Family, it's pretty slim. Let's change the scenario just a little bit. How about a bear falling backward? Same distance while smoking.
2,200 volts of electricity.
Do you think this is survivable? Yes or no? All right, guys, it's the same distance.
Yes.
All right, all of a sudden you're thinking the dogs are not going to be able to survive this, but the bear may be able to survive this. All right, so do you have an explanation for it?
The bear's unconscious, so at that point his body would just be kind of limp.
Okay, I'm going to give you 5 points for that one. That was a really decent explanation. If the bear is unconscious, what happens to the muscles? They're relaxed, guys. So what does it mean? Which means that the bear's impact time is going to be relatively large. All right, so the relaxed muscles will only increase the impact time. So that may be survivable. That may help bear survive something like this. That's one explanation. You can still come up with 4 more reasons as to why the bear may be able to survive this. So we'll investigate that. So falling objects. Do they follow a constant speed or do they accelerate? What do you guys think? All right, this is a simple demonstration. You guys see the ball, right? All right, so while you guys are watching the ball, do you think that the ball is speeding up or do you think it's falling at a constant speed? What do you guys think?
Constant.
Okay, but one thing that I'm hearing is some of you guys say constant and some of you guys are thinking it's speeding up. But the reason is because you're not going to be able to tell. Okay, whoever said anything or put anything on the chat, give yourself 2 points so far. Okay, is it speeding up or is it falling at a constant speed? You can't tell by looking at it. Unless you're high on something illegal, then obviously you're going to be hallucinating. You'll probably see some traces that will change color and whatnot. And then you'll also see some angels or devils or whatever. Demons. All right, but there's enough information here for you to be actually, visual information here for you to be able to conclude something. What is it? There's something that happens that tells you that this is either speeding up or it's falling at a constant speed. So the question is what? Which one? All right, here, say it again.
Gravity.
Forget gravity. All right, guys, is it speeding up or is it falling at a constant speed? Okay, notice that it goes from 0 to something else. Do you guys see that? It goes from 0 to something else, so which means that it's accelerating, right? If it didn't go from 0 to something else, you wouldn't need a parachute when you jump from an airplane. You would be stuck up there unless someone came to your rescue. You would starve to death. Do you get it? So falling objects do accelerate. Where's the evidence? Well, they go from 0 to something else. Okay, now when I throw the ball back up against gravity, do you guys notice that it slows down? It slows down to a stop. So that's also acceleration. So the falling objects do accelerate. How do we know? When drop will go from 0 to something else. And also, we know that throwing up against gravity, it will slow down to a stop. So the falling objects do accelerate. An experimental verification of it, when dropped, they will go from 0 to something else. and thrown up against gravity, it will slow down to a stop. All right, that's it. Okay, got the best answer? Place it in the chat. Okay, very good. C, C, C. Okay, so falling objects will speed up, right? So speed is going to go up, direction is the same, so the velocity is going to increase. So C is the best answer. Give yourself 5 points for that one. All right, so the next question is, the falling objects, do they fall at a constant rate of acceleration, or does the rate of acceleration vary depending upon the weight? This requires a bit of a demonstration one more time. All right, so does the rate vary depending upon the weight? Okay, let's do a simple experiment. Does you guys see the piece of paper and the ball? Now, remember, guys, this ball is like 1,000 times heavier than this piece of paper. So when I drop it, which one is going to land first? Well, you know the answer, so let's just do the experiment demonstration. All right, notice that the ball ends up falling much faster, right? All right, so the question is why? Why is it that the ball is actually falling faster than a piece of paper? Now, you can come up with 2 answers for it. So what are those reasons?
Air resistance.
Give yourself 5 points. The air resistance may be a factor. The other is...
Even if the drag was the same, the ball has a higher mass, so the air resistance won't have as dramatic an effect.
So I'll give you 5 points for that one. The air resistance is a factor. Also, the weight is a factor in this case, right? All right. So the question is, which one is a factor? Okay. So I got 2 pieces of paper, same size, same shape. They weigh the same. If weight is a determining factor in terms of how fast an object is going to fall, then because they weigh the same, they should fall at the same rate. Right? That's what it means. So if I were to grab one of the papers and just crumple it, I'm not changing its weight. It still weighs the same. So if weight is a determining factor, when I drop them from the same height, they should still accelerate at the same rate. But when you do the experiment, immediately you notice that air friction is a factor, so it's undeniable. All right, so the crumpled paper ends up falling much faster. So the question is, what happens if the effects of air friction becomes negligible? Does weight a factor under the circumstances? Guys, crumpled paper, and you got the ball. Remember, this ball is still 1,000 times, more than 1,000 times heavier than this piece of paper. And also, I want you to remember that this piece of paper, because it's crumpled up, it doesn't experience a lot of air friction. It doesn't experience a lot of drag. So do you think this piece of paper is going to fall at the same rate as a ball, which is about 1,000 times heavier? Okay, let's do the demonstration. All right, I'm going to drop them, and they will just disappear from your view within 4/10 of a second, guys. So don't blink. Okay, so let's do the experiment. I'm just going to drop them from here. And you guys were able to see a blur. Within the blur, what do you guys see? Within the blur, you notice what happens. They're falling at the same rate. Isn't that weird? All right, so when the effects of air friction becomes negligible or ignorable, the weight doesn't matter, does it? When gravity is the only force acting, weight does not matter. That's what it is. So that's known as free fall. So all objects will fall at the same rate of acceleration when the effects of air friction is negligible or ignorable. I mean, if we were to do the experiment at the surface of the moon, this piece of paper, and this ball would still be falling at the same rate. In fact, we did the experiment at the surface of the moon. One of the last visits to the moon.
Explored the airless surface of the moon. He couldn't resist repeating this classic experiment for all the world to see.
Well, in my left hand, I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
All right, guys, except the difference between what I did and what they did is that cost us like $1 billion. It's the same experiment. Galileo is the guy who came up with that, believe it or not, 400 years ago. He's the father of science. He's this guy who said, hey, if you got a theory, make sure that the theory makes predictions so we can test those predictions. It was in his 70s, under house arrest, life was boring, and that's when he decided to conduct his experiments, physics experiments that we know him by, basically. So he's the one, he said, hey, only in a vacuum, in an airless environment, or when the air friction is negligible, all objects, regardless of their weights, will fall at the same rate. That's it. Now, the rate at which the object accelerates is known as g. All right, so this is the acceleration due to gravity. And notice that it's 10 meters per second squared. Remember, we were expressing accelerations in terms of your own body weight? All right, that's where the term comes from. All right, so 1g is going to feel like your own body weight, in essence. It's roughly about 10 meters per second squared. The actual number is 9.8 or 9.81, depending upon which book you use or where you do the experiment. It may vary just slightly. All right, so the weight doesn't matter, which means that both objects will hit the ground at the same time. So C is the best answer. Give yourself 5 points for that one. All right, so for relatively heavy objects, for relatively short distances, air friction is negligible. All right, so when we go back to slow motion, all right, so the ball is here, its center of mass is located there. Notice that there's relative position remains constant. So for relatively short distances, for relatively heavy objects, friction usually is negligible or can be negligible. Okay, so let's do have a mathematical modeling here. So far, we talked about uniform motion, uniformly accelerated motion, which means that the acceleration is constant. It's going to be speeding up in this direction within this distance and within that time period. All right, so we were able to describe this motion using 3 equations. Okay, real fast, guys. What's the meaning of the first equation? I'll give you 5 points for that one. What does the first equation tell us? All right, so race, I need more than that. I'll give you 2 points for that one. Okay, first equation is going to locate object for you at a given point in time, right? So if you know the time, you know exactly where the object is. Okay, Juan, give yourself 5 points. Jessica, likewise. Okay, so if you know the time, you know where the object is, right? What does the second equation represent?
How fast it's moving at a given time.
Yeah, give yourself 5 points. It's how fast it's moving at a given point in time. So if you know the time, you know how fast it's moving. What's the meaning of the third equation?
Speed at that location in time.
Speed at that location. Give yourself 5 points. Very good. All right. So you guys are actually putting stuff on the chat once again. Give yourself 5 points. All right. So immediately, the location becomes predictable for a given time. Speed becomes predictable at that time as well as at the location. That's it. Okay. So what do we know? In free fall, we know that the acceleration is going to be constant, right? It's the same as uniform acceleration. This time it's along the y direction. So this thing is going to follow a certain distance within that time period while accelerating in the downward direction. So what we'll do is we'll just modify the equations. All right, so we'll use the same 3 equations, except the letter x is going to turn into letter y. It's going to turn into g. And the initial and final velocities will be initial and final velocities along the x and the y directions. That's it. So we'll just modify the formulas. We'll take the same formulas and just modify them just a little bit. All right, notice that this is y modified from x to y. And once again, this gets modified using the transformations from there. And that's it. So in essence, these formulas are identical to those formulas. So now these become the free fall formulas. That's it. All right, so give me the interpretation of the first one. I'll give you guys 5 points one more time. So, all right, so what's the meaning of the first formula? Okay, very good. If you know the time, you know the position, right? You know the time, you know how far the object is falling. You know the time, you know the vertical position of the object. You know the time, you know how far the object is falling up to that point. Okay, what's the meaning of the next formula? Okay, very good. Connor says, you know how fast it's falling at that point, right? You know the vertical speed at that time. Very good. So you know the vertical position at this point, you know how far the object is falling, and you also know how fast the object is falling at that point, right? So what's the meaning of the last one? Yeah, very good. Vertical velocity at that position. So if you know the position, you know how fast it's moving at that position, right? So the first formula is going to tell you how far the object is going to fall within this time period. It's going to tell you how fast it's going to be moving at that time and at that location. So that's it. Once again, the motion itself is 100% predictable.